Thank you very much. Thank you, John. You made a great introduction. My talk is titled Learning and Memory in Human and Artificial Brains, and you basically just described my first slide over here, which is talking about three aspects of my research. On one side, you're doing some behavioral studies to try to understand the core principles of memory and learning. We are also looking at electrophysiological data to try to see neural underpinnings behind what we see in the behavioral experiments and try to put all that into computational models, including deep learning models, to try to build systems that on one side can take inputs similar to those in animal experiments, in human experiments, when it comes to behavioral electrophysiology, but also produce behavioral outputs like those in humans and neural activity like what we see in the animals. So this is roughly also the structure of my talk. I'll start a little bit with the behavioral data to give us some insights about the specific perspective on how the brain represents, in particular, mental maps, structured representations, then looking into neural data and trying to build some models from that. So just to start, thinking broadly in terms of how do we compute, how do we represent information, I would argue that we do that in a structured way, that we build these mental or cognitive maps. And if I ask you, it's, I think, relatively easy to convince yourself of that. If I ask you what's the layout of your apartment, you can probably create some sort of a mental map of different rooms and corridors, how they're connected, etc. But critically, we can also compute with those mental maps. So if I ask you, for example, to navigate from this room to the restroom, in this case it happens to be particularly easy because as I learned it's just over there. But you can kind of imagine a trajectory of going from where you are to the place where you want to be. Similarly, regarding the computations, if I ask you which country is bigger, UK or Spain, unless you know the answer by heart, you may imagine mentally translating the map, say, of Spain over UK and kind of rotating and trying to compare the surfaces. Or is this letter here R, or is it a mirrored version of letter R? That's another computation. We can all kind of mentally rotate and see, okay, it looks that way, so I believe it's a mirror. And importantly, these types of representations, these structured representations, may not be there just for space, but for knowledge in general. So, for example, if I ask you which of these two tones is higher, beep or beep, or if I ask which of those two tones happened more recently, so we have also this temporal dimension, and I'm going to talk much more about that, or in a completely more abstract space, is a tiger more ferocious than a bunny? We can do comparisons, we can apply these operations seemingly across all kinds of different domains. And I'll really start with this example of temporal recency and then generalize that to spatial domain and also to more abstract domains. To start talking about time, let me describe a behavioral experiment called judgment of recency. In this experiment, which first time I think was done back in the late 70s, early 80s, and people are represented with a list of letters one at a time, and then they are probed with two letters from the list and asked which of the two letters was presented more recently. So it's a typical temporal judgment. They need to indicate which letter they think was presented more recently. Actually, to get a better sense of it, maybe let's do the task together. So I'll present you a list of letters one at a time, and then two letters at the end, and I'll ask you to make that temporal judgment and tell me which of the two was more recent. So pay attention to the letters on the screen. I'll try to mimic the presentation rate with my slider, with a clicker here, but may or may not be exactly as in the experiment. G or T? Any guesses for G or T? I hear some G's. I believe G was, I believe for folks who thought G were correct, G was more recent, so that would be correct answer. Participants are reasonably good at this. They are well above chance, not perfect. But there are two particularly striking properties coming out from the response time results. So the most interesting part here It's not really accuracy, it's more the response time, how long it takes them to press the button to make the decision. On one side, the response time depends only on the lag of a more recent item. So here we have G and T. T is further in the past. The response time depending only how far in the past was G. It's consistent with the hypothesis that there is some sort of a mental timeline, and what participants are doing is kind of scanning this mental timeline until they find a match, and that's when they press the button. And then, second really intriguing property, I think, is that the response times grow sublinearly with the lag. Basically, it takes you longer to navigate from -1 to -2 than from -2 to -3, then from -3 to -4, etc. It's consistent with the hypothesis that the more distant past is compressed, that the representation is more compressed. And in particular, it is relatively well fitted with a straight line along the logarithmic axis. So as if it was logarithmically compressed, consistent also with the Weber's law. So if we want to think of it from computational perspective, we can just, in general, imagine a very simple model in which each letter in the sequence would have a set of units, let's say neurons, that activate sequentially after presentation of each letter. So if you have R on the screen, imagine you have a sequence of units that will activate after R. So after R, there's Y, but these neurons here start activating, and these neurons propagate further, activate further, so indicating that R is now further in the past. And as we go throughout the sequence, this representation sort of fades into the past. And when the probe comes in, when P and G are on the screen, one could imagine some scanning from more recent past toward more distant past. And if this representation is compressed such that the distances here for the more distant past are not as large as distances over here, then we would get those same behavioral properties. I'm going to formalize this later for a mathematical model, but this is just to give an intuition that one could imagine a sort of, I will call this a timeline, that sort of encodes what happened when. And the utility of this representation could be primarily in the power to build associations relatively easily. So for example, if we have a stimulus, like some tone or a bell, and if there is a set of neurons that activate sequentially following that stimulus, then at the time when the reward is presented, just simple Hebbian associations can create a link between the neurons that are currently active, like these over here, and the reward. So next time when the bell is presented, if such representation is available, one can predict when the reward is going to happen. This is, of course, a relatively simple scenario in which you're just having two stimuli and everything goes orthogonal, so it's relatively straightforward, but we'll see later a little bit how we can generalize it more. But this in particular makes assumptions on how this representation is used for predicting the future, and we, in addition to that judgment of recency, designed another experiment, which is called, we call it judgment of imminence, and it's trying to mirror this judgment of recency. But in this judgment of imminence, participants need to predict something. Basically, they need to tell us which of the two letters is going to happen sooner in the future, which one is more imminent. For that to make sense, we first had to train them on some sequence of letters. Once they become familiar with that sequence, we can interrupt the sequence, so it's still one letter at a time. They see the sequence many times. We occasionally interrupt the sequence and show them two letters from that sequence and ask them which of those two letters is more imminent, which one is going to come sooner. And what we see is very similar to what we saw with the judgment of recency. The response time now depends on the lag of a more imminent item. It's as if the participants are scanning from the present towards the future until they find a match and then they press the button. And it also, again, grows sublinearly with the lag. It's as if whatever they're scanning is more compressed in the future. If we put them side by side, the past and the future, we see that in general, qualitatively, this looks similar. There were some methodological differences between the two tasks, in particular related to the presentation rate. So there are differences over here in the response times as well, which may be due to the different times taking to complete these operations, or it might be something to do with our methodological differences. So I can't put too much emphasis on the quantitative comparison. We are doing some of the experiments along these lines again to specifically compare the scanning rates, basically the slopes of these lines over the past and future to see whether they're faster or are they having equal pace as they're navigating either past or the future representation. One can think of it just computationally on a very high level. If we have a representation, we have some three stimuli A, B, and C. After B is presented, memory of A is somewhere over there. When C is presented, then memory of B and A is somewhere in the past. So just through associative learning of linking B with A over here and C with B and A, then next time when A is presented, we can construct a similar timeline of the future. And so by navigating that timeline, basically we get the response time that we see here. Again, we'll formalize this more, but this is again on the intuitive level. So this was our motivation in terms of the behavioral experiments for this mental map for the structured representation of the past and the future. And I forgot to say earlier, if you have any questions, feel free to interrupt me anytime, so just let me know. I'll shift the gears slightly to dive into the electrophysiological zone to look into neural activity that could relate with this type of structured representation. And this is just a general example of an electrophysiological protocol. I'm sure you're familiar with this type of recordings where there's behaving animals activity. In particular, in our case, most of the recordings we're going to look into are from the hippocampus, but also some from prefrontal cortex. And we're going to look for representations of neurons that are related to these map-like structures, in particular representations that are similar to famous place cells, but code not just space, but also different dimensions. So, in particular, we are noticing a common pattern for encoding different variables, including space over here, time. This is sound frequency, which in this particular task was a task-relevant variable, and this is amount of evidence in a task that animals had to count. So specifically, this task on the left, animals are just navigating a linear track to get a reward, and what we see here in each row is activity of an individual neuron as a function of the distance along the linear track, and you can get the gist here that there is a sequential activation of these units. They're basically one-dimensional place cells. They tune, they activate highly for a particular range of the track. Now, in a very different task, in a temporal dissection task, where animals had to wait over here in this little area, they wait until the little bridge goes down, and then they can cross. Now, the time that they spent waiting before the bridge went down, they have to keep track of and go left if it's lower than a certain amount, and go right if it's larger than a certain amount. So it's a temporal dissection task. What we see during the waiting period is, again, a sequential activation as a function of time. Again, each row here is an individual neuron, and the color represents the activity of the neuron. Here is a sound frequency estimation task where animals were presented with a tone of increasing frequency, and they were trained to press the lever when the frequency would reach a certain range. So, and the rate of increase was deconfounded from time, so they could not just time it. They really had to learn that, okay, as the tone is increasing in the frequency, when do they have to press the button to get a reward? And this is recording from the hippocampus, which normally you would not really expect to be some musically tuned area, but here we have neurons, again, that activate selectively for particular sound frequencies. And this last task over here is the counting task, so-called Towers task, where animals are in virtual reality, so they're running on a little sphere, and they see a corridor with some objects on the left and the right-hand side wall, and at the end of the corridor, they have to turn left or right, depending on which side had more of these objects that are referred to as towers. So it's an evidence accumulation task. Every time you see an object on the left-hand side, it's an evidence for left, right-hand side evidence for right, and at the end, you have to make a choice and see and compare and turn left or right. And again, folks have reported neurons that are selectively tuned to, in this case, magnitude of the evidence. So basically difference in the number of these towers on the left and the right hand side. If the number was the same, that's 0. If there were much more evidence to go left, that's over there. Much more evidence to go right, that's over there. So again, neurons tuned to whatever is the task relevant variable. So seemingly across different domains, these are sort of similar coding schemes, similar representations. Yes?
Why is it, or at least it looks like on the sound frequency graph, that the neuronal firing is so much more noisy than the rest?
This one looks much more noisy?
Well, at least on the horizontal grid, you can see that there's some more firing than on the VR side, right?
It's hard to say. There are a number of reasons. On one side, each of these rows represents average activity across many trials. I don't know by heart how many trials, for example, was it in this recording. Also, while I selected here these 4 heat maps, across the literature there are dozens right now. People have started using this type of representation more and more commonly. But there are different ways how they do that. For example, in some cases, there are neurons that are selected. For example, in this work, we selected these neurons using a maximum likelihood model to compare neurons tuned to time versus neurons tuned to other variables, etc. So we are showing a selected subset of cells, while in some other work, people would show just all of the cells, which I think both is valid, and it's important to see what all of the neurons are doing. There are also various ways to analyze these. For example, plotting just even trials versus odd trials to see whether there is some sort of random effect. The important thing here is that everything is sorted based on the peak time, so no matter what, you would always see some sort of trace along the diagonal. So it's important to do different types of controls for that as well. Now, given these types of results, we tried to look at, from the computational perspective, how we can build a model that can give rise to those types of cells. So if you have this example here with temporal dissection, we see sequentially activated neurons. How we describe it to ourselves is that, well, let's say there is some input at time 0. What we want is to see a set of cells that activate sequentially, that become broader in their activation fields as the time elapses. In particular, in order to account for those behavioral results we saw recently in the judgment of recency and judgment of imminence, we want this to be log compressed in the sense that if I printed log time instead of time here, then these receptor fields, these bell-shaped curves, would be equally wide and equidistant. So it's sort of uniform spacing over the log time. Over the mean time, then the width is increasing proportionally to the peak time. Now the question is, how do we build a neural network, a system that we can describe in some equations that would give rise to this? And I'm building here on a Shankar and Howard computational model. So if some of you have seen maybe Mark Howard talking about a Laplace transform framework, then this is that same mathematical framework. To go from here to there is basically an intermediate layer of neurons that decay exponentially, that give an impulse response, that decay exponentially with a spectrum of time constants, so some decay faster, some decay slower. We can describe that through a simple leaky integrator equation, so the firing rate decays exponentially. The solution of this equation gives us exponential decay with the rate constant s. A simple linear transformation from this layer gives us a set of sequentially activated cells. Now, the intuition behind this is that if we have some input and then we feed it into a set of cells that behave as leaky integrators, that decay at spectrum of time constants, we are effectively approximating an integral transform. If we would have infinitely many cells here, I would argue that this is exactly like the real domain Laplace transform. So it's an integral transform, meaning that no matter what function was here at the input, if we have infinitely many cells with all the time constants that receive that input, then all of the information about the input would be stored in the activity of those cells. And doing this projection here is nothing but inverting the Laplace transform. So as the output, we get also a set of neurons, but activity of those neurons exactly approximates the input function. If you would have infinitely many neurons, then it would exactly reconstruct it. In this case, we're doing an approximation of the Laplace transform with a finite number of neurons. So our reconstruction is also an approximation, and it's an approximation such that it's more precise for the more recent past than for more distant past. So neither the brain has infinitely many neurons, neither we have perfect memory, but with this approximation, we can get something that is consistent with the results we're trying to capture. I'll represent the same thing just with a little different graphics to give you a little different perspective on it. So let's say we have two delta pulses here, two stimuli, let's say, presented to the system, and then we have a set of neurons decaying exponentially in the response to the first stimulus, then those same neurons later decay exponentially in the response to the second stimulus, and if we do this inverse transform, we get sequentially activated neurons. Now, if we take the activity of these neurons at some moment in time, let's say here in time 10, and then plot the activity as a function of the peak time, which I'm labeling here as T star. So each of the neurons over here has some characteristic peak time, which we can compute analytically from those time constants of the exponential decay. So for every neuron, there's this characteristic peak time. And if I plot its activity, or activity of all of these neurons, as a function of that peak time, what I'm effectively building is like a mental timeline that tells me what was at the input certain time ago. So it tells me, okay, there was a peak around here, and then there was another peak around there, but the temporal precision of this second peak is much lower. It's fuzzier. I'm not exactly sure when it was. This is like my distribution of, I think it was somewhere around there. If we had infinitely many neurons, this would be a perfect reconstruction, so I would get exactly two delta pulses because it would be Laplace and inverse Laplace transform. Mathematically, it would be literally a perfect memory. In this case, it's a log-compressed version of it. And because the system itself is linear, the leak integration and this inversion, which is just a matrix multiplication, everything is linear, so the outputs of the system are just convolutions between the impulse responses, so these bell-shaped functions, and the input. If the input is much more complicated function of time, like something like this, the output, those activity of these neurons, would still be an approximation, a log-compressed version of that signal. So it would have high fidelity, high temporal resolution for the more recent past. Presumably this is the end of the signal, so high resolution here, and then gradually decaying resolution for the more distant past. So these orange dots would be a memory of the input signal of the blue trace of that log-compressed system. So the system, if instead of these two delta pulses, we had the blue line with many squiggles, this would be an approximation. We took this as a building block of a reinforcement learning agent systems, just to see, okay, can we plug this into a learning system, like a general deep neural network, reinforcement learning type of agent, reinforcement learning agents, where we feed in the exact, or at least a similar environment to what the animals have experienced during training. So animals were in this environment with this bridge going down, but they have to wait and then turn left and right. So this is the temporal bisection task. So animals have to keep track of the elapsed time and then take a left or right turn when some stimulus happens. In this case, when this bridge goes down, the animals have to turn left or right. So we take that environment, pixel observations, we feed them into some encoder, which is some convolutional neural network, and then feed that into a recurrent network. Now, typically in deep learning, people would put here just a regular RNN, regular recurrent neural network, or maybe some of those long short-term memory LSTM network, or something from the arsenal of deep learning, and then train it with some reinforcement learning objective function, which is just trying to maximize the amount of reward. In our case, instead of this standard recurrent memory, we feed in our recurrent memory, which is this model over here. So this is still a recurrent neural network technically, but if these weights are derived analytically, these values, these time constants that decay, they're not trainable. So they just encode temporal history of this. So they're not trainable, unlike in a regular deep neural network. When we look at the performance, then these agents can in general learn well. They can learn faster than their standard deep learning counterparts. We can observe, we can look into neural activity. So this is the agent doing the task, so navigating this and then turning left or right at the end of the corridor after the bridge goes down. And we can look at the neural activity and compare it this is just a general plot of the activity of neurons in the encoder and the recurrent layer. But we're going to look more closely to compare it with the brain activity. So this is the neural data. The recordings here are primarily from the prefrontal cortex. There's actually several areas of the prefrontal cortex that are in this data set. And we see the sequential activation. If you look at the activity of the agent, this F tilde corresponds to our model, the green line over here. That's our cognitively inspired, if you want, neural network. These are those standard deep learning agents, LSTM and RNN. In general, this is kind of by construction in this case. With F tilde, we're getting sequential activity that is much like the brain because there is nothing learnable in that recurrent network here. As long as it learns to extract the stimulus, it's just going to have this sequential activation. While other networks are also going to be able to learn a task if they're trained for long enough, but they are going to have different type of neural activity. So this is just an illustration that, okay, with this type of architecture, we can get on one side good performance, and on the other side, it's consistent with the activity in the brain, so that maybe this type of representation is easier to use. I will go ahead.
What does the neuron that you're plotting correspond to? Is it the hidden state?
These are the hidden states of the units in this particular network. So the activations of these units. One caveat here is that we have this nice structured representation, but it's actually here fed into a dense layer. So it's fed into something in a deep network that just loses that structure. It doesn't really exploit it. Meaning deep neural networks, like quite literally what happens here, become a nice structure, and then we multiply it by a random matrix. Because that's what the dense layer is. It's that random matrix gets trained, but at the beginning it is really just just a random matrix to compute a policy, to compute the value within the standard reinforcement learning frameworks. So this is something that we are still working on, that we need to do better, and that is to exploit the structure that we have from the neural representation in a more efficient way. It already seems like it's beneficial, but it's undoubtable that we can think of something that takes better advantage of the structured representation. I'll give some more examples later, but this is just kind of as a caveat. Yes?
In the reward plot, your model kind of hangs out around 0.64 on the rapidly shifts to 1, where the RNN kind of more gradually increases. Is there a reason for that discrepancy?
I wouldn't look too much into it, honestly. There are so many different hyperparameters that can influence this. So when we run these, we typically run hundreds of them with different hyperparameters, and then for each type of model, we select the best performing ones. So maybe we could have found some that would learn a little faster, but maybe wouldn't reach the plateau as fast as this one. So one of the things that I've learned from using these types of policy value standard LLM frameworks is that are extremely dependent on the hyperparameter choices, and you really need to optimize quite a bit. So the different types of variability often then end up being very difficult to explain. So I don't have some good explanation on why, say, this one would learn a little slower than the other ones. But it is a good observation. We've also tried using these in the context of machine learning applications. So in particular, for time series prediction. So let's say we have some time series of some signal. We can construct, as we described earlier, a logarithmically compressed version of that signal, where each of these circles represent a neural activity, so activity of an individual neuron, and we have a set of those. So by feeding them through this network we described earlier, given this input, at this time, at time 2000, we have a set of, let's say, 50 neurons, and these circles, the magnitude of the circles represent activity of those neurons. So let's say if I have 50 circles, then this is 50 neurons representing activity, representing values of this function throughout time. So it's sort of a low compressed memory. Now, you can think of it as basically an output of filtering this type of this signal with impulse response filters, which are very narrow for the more recent past and just broader and broader for the more distant past. So that is equivalent of what we are doing, except we are doing it with a recurrent neural network, so it is time local, but it's effectively like the output for this case would be like having a filter bank and producing the output in that way. If we put in this type of a module inside of deep neural networks, so literally make it like a layer and then stack them up in a deep sense, then we can evaluate the performance on some standard machine learning benchmarks that people use for time series prediction. And I'm going to show you just one of those. It's the adding problem. Adding problem, the input consists, it's a very fake problem. It's just designed for people to compare time series prediction. In particular, takes into account long temporal contexts. So the input is two-dimensional. One dimension is binary, just 0 or 1. And it has exactly 2 ones. So everything is 0 except at 2 places it's 1. Here it's represented by these 2 x's. So everything is 0 for the red signal except these 2 x's. And the other dimension, so the signal has 2 dimensions. One is 0, 1. The other dimension are these blue bars. So they're just some random numbers between 0 and 1. And the output, the system has to produce the output that is the summation of the values corresponding to the red axis. So somehow the system has to learn that when the first dimension is 1, then you have to remember that number. When the first dimension gets 1 again, you have to remember that number and add it to the previous number, and that's your output. It's kind of simple for a person. This doesn't seem like a very difficult task, but the tricky part is that we can change the number of time steps here. So if we make it very long, so then for recurrent neural networks and other approaches in deep learning, it becomes more and more challenging. So I won't go into too many details with the results, just show you a brief outline. The proposed approach with this log compressed memory, it's quite robust to rescaling. So if we increase this duration, because the amount of resources just grows as a logarithm of the interval that we want to represent, it's fairly robust. And it was able to learn at different scales, so whether this whether this t, basically the length of this sequence, is 100 or 500 or 2000 or 5000, it was able to learn the task relatively well, while other approaches are doing well when the intervals are relatively short, but then when they become relatively large, then they just in general fail or learn much slower. So there's, in general, conceptual advantage of just building this log compressed representation that doesn't really require trainable weights and backpropagation through time like what is done in the common deep learning models. I'm not saying that this would work for absolutely everything, but on these typical benchmarks that we tried on, it performed pretty well. Another interesting property of this, another example, is using the log compression for invariance to time rescaling. And it's on one side, this is very much inspired by the processing in humans. So if I see that I'm running out of time for my talk and I still have too many slides, I may just start speaking twice as fast. Promise not to do it. And you would still be able to understand me. People are pretty good at generalizing when the input is rescaling. We're also pretty good at generalizing when the input is rescaling when it comes to vision, so we can recognize the object when it's larger or smaller. We don't have to have explicit training data at every scale, every size of an object to be able to generalize. Our retina has effectively roughly log polar spaced receptors, similarly to what we are proposing here as this computational model for log compression. And to illustrate how this works, what's the idea of using this to get invariance to rescaling? We're going to consider this example with 2 signals. So the red signal here and the blue signal, which is just twice as fast. So it's the same functional form, just instead of 2 and 3, we have 4 and 6 over here, it's just twice as fast. If we construct the log compression of both of them, we get something like this. Again, these circles represent neural activity at time 2000. And let's say here maybe we have 50 neurons, so there are 50 of these circles. They basically tell us at time 2000, this is our log compressed memory. Now, each of these circles is plotted against the peak time of these neurons. So we said we can analytically, for each neuron, compute the peak time, and we can then plot this as a function of those peak times. And they're log spaced. However, if we plot this as a function of the index of the neuron, we're effectively undoing that log spacing. So in that case, because of this mathematical property of the logarithm, that log of a times x is log of a plus log of x, we're effectively turning rescaling into translation. So the blue and the red are now translated version of one another. And in fact, if we just do that translation, if we translate it, to translate the red by minus log a, so if we translate it by the scale, then the two lines are just going to overlap. They're not going to overlap over there. There will be some edge effects, but the majority of the line, the part that's everything besides the edges, is going to overlap. So in the context of deep networks, if we think of it as, well, these are two translated, we're able to go from rescaling to translation. Translation, if we put a convolutional layer and then max spool, so we just take a large window and average it, then we can achieve invariance to translation is relatively easy to achieve. Invariance to rescaling is hard, but if we are able to move rescaling into translation, then using convolution and max spool, we can achieve invariance to the translation. So we took that architecture together with the convolution and max spool, convolutional layer and max spool layer, and again built it into a deep neural network, stacked many of these layers, and then applied it to some standard machine learning benchmarks where we tweak them to test ability of deep neural networks to generalize to rescaled versions. So in this case, I'm showing an example of spoken MNIST. So MNIST is a commonly used computer vision data set where people have written digits with many 70,000 handwritten digits. It's very standard for computer vision. But there is another version of that data set called audio MNIST where people speak the digits. So they just say 7, 5, 3, and you have a lot of recordings of that. Then we train our network on those spoken digits, just as a supervised learning classifier. You know, a bunch of examples of 5, and then label 5, etc. And then we evaluated on that same speed, but also on other speeds. So we changed the speed of the signal to be twice as fast or twice as slow, for example. Put the signal at a different scale. And our approach, the blue line, was in general able to be robust to that rescaling, up to these edge effects and up to the bounds that we had with the minimum and the maximum value of our filter. So we kind of determined the upper and lower edge to which we want the system to be invariant, but within that range, it was invariant to rescaling, unlike some standardly used approaches for that type of problem, like temporal convolutional network, which can do a perfect job at the scale that it was trained on, but it could not generalize to other scales. This is something that arguably could also be translated into the vision domain. There was some work along those lines as well, and we're working with that also. So that's another sort of machine learning benefit in terms of building these invariances to rescale. Let me know if you have any questions. I'll move on to generalizing this approach. Everything I told you before was related to time. Now we're going to talk about how to generalize this to other domains, in particular starting with space. So the intuition is relatively straightforward. If we have some delta pulse and we have a set of neurons that exponentially decay, if we modulate the rate of that exponential decay with the velocity signal, so let's say I'm moving fast, then this is decaying fast, then I stand for a little bit, then I'm modulating the rate of decay with the velocity signal. So if my velocity is 0, then this derivative is 0, so this is not moving at all. Then if I move again fast, this is decaying fast, moving slow, decaying slow. Then what we effectively did is turn exponential function of time into an exponential function of traveled distance. Now this same inverse transform will no longer give us nice bell-shaped sequential activation in the time domain, but if we plot it as a function of distance, then it's going to be exactly sequentially activated. Somewhat resembling again the one-dimensional place cells. So these are place cells in 2 dimensions. In 1 dimension, they would presumably look something like this with this log compression effect. We can turn time into other variables, not just spatial distance, but anything that we have a derivative of, or anything that the derivative of can be extracted from the environment. So in this example here, we have evidence, or the amount of evidence as modulator. I should say actually change in the amount of evidence. So in that task I described earlier, the towers task where the animals are running down the corridor and see objects on the left and the right, if we imagine that every time when the animal sees an object either on the left or the right, that is the change in the amount of evidence, and we can represent it with a delta pulse, then the exponentially decaying units are only decaying when there is new evidence. So if you do the inverse transform, now the activity, the sequential activity will no longer be bell-shaped tuning curves as a function of time, but bell-shaped tuning curves as a function of count, as a function of, say, how many objects has the animal seen. And that type of representation can then be used to construct something like this. So these neurons observed in the hippocampus that are selectively tuned to the count. The larger picture is that if you're able to somehow extract from the environment whatever is the derivative of the latent variable, we can modulate this temporal representation and construct bell-shaped tuning curves of that latent variable. And we went along that route to try to see if we can learn. So this is modulating the rate of decay. So this is gonna injecting into these recurrent weights. So the recurrent weights on one side are non-trainable, but there is something multiplying them that we can turn into trainable. So in other words, we can feed the inputs of the system, like pixel observations, into a neural network here that learns how much to modulate the rate of decay of these exponential decaying cells to basically see if it can learn what is the latent variable that needs to be represented. So to do that, we constructed a pixel version of this environment, like a video game. So the animal is navigating, not the animal in this case, the artificial agent is going to this virtual track, seeing these objects on the left and the right. The input observations, the pixels go through a standard convolutional neural network, and then the outputs of that network are going into the recurrent weights of this layer. So they're multiplying the recurrent weights, basically choosing how fast this representation decays. Note that it's always the same factor multiplying all of the recurrent neurons. So in general, in deep neural networks, neurons are not really playing together, right? You have a bunch of them, they're distributed, and there's a gradient, and you're updating these weights depending on the gradient. Here we have a set of neurons that kind of tied recurrent weights. They're in a relationship, and when we are modulating that, we are modulating all of those weights. So in that case, our neurons are always structured, meaning that there is a metric space. Neuron 1 is always activating right after neuron 2, which is activating right after neuron 3. So unlike in regular deep neural networks, which are definitely not addressable, in this case, you really get a system that is addressable in the sense that you know that if this one is activated first, this one is activated after, etc. So you can imagine doing different types of operations on top of that. I'm not going to talk about that, but there are other advantages of having the Laplace domain. For example, in terms of compositionality and in general building representations from this. So you have structured representation, sequential activation. You can imagine you're in the Laplace domain. Operations like subtraction, which can be implemented through convolution and cross-correlation, just become products. The larger picture, having structured representations, we can learn functions and apply those functions, which are then, because the representation is the same for different domains, those functions can then be applied to those different domains. So if I know how to subtract frequencies of two tones, I can also subtract two distances, I can also subtract two times, etc. It's the same representation. I don't need to relearn it again and again and again. But in standard deep neural networks, those are always different representations. These neurons are always different. Therefore, any operation that we are learning would have to be relearned again and again. When we plug this into a deep neural network, and then again, this is actor-critic kind of standard reinforcement learning, still suboptimal because these networks are not really taking full advantage of the structure. This is how it looks like when the agent is trying to solve this task. So you're seeing some towers, and then at the end, it will turn left or right. This is a neural activity, but we can look at it a little bit more systematically. The performance in general for these agents is this is depending on a lot of these hyperparameters, etc., different configurations, but in general, our agents can learn reasonably well, similar to these LSTM agents. And in terms of neural activity, you can see that this is what's recorded in the brain by David Tang's lab. And these are our agents which exhibit this kind of similar sequential activation as a function of the amount of evidence. Other agents also able to learn the task, learn different type of representations, like these ramping structures, for example. But these are designed to effectively learn the same type of representation, neurons that are tuned to a particular amount of evidence. Again, we are still not using we're not taking full advantage of the structure, but at least we're building it so hopefully down the road we can see how to learn better and more efficiently with this. So this is still ongoing work, and in the next couple of minutes, I just wanted to give you a quick overview of a couple more projects that I didn't have time to dive into more detail. So this is going to be just a quick shout out of a few recent papers and ongoing work that I think some of you might be interested in. And my first highlight here is training machine learning models using infant egocentric videos. It says curriculum matters. And this is a collaboration with Professor Linda Smith at Indiana University. Linda has a data set where infants are wearing head-mounted cameras. So this is a camera out there, and just going about their daily life. And basically the instruction to the parents is just do whatever you normally do and just turn the camera on. That's it. We are interested to see whether what is in the data and how important it is, because we know that this is in particular for infants 2 to 24 months, where the motor properties are drastically changing. So the properties of the visual inputs are also drastically changing. And we are trying to understand what is in the data and is it actually developmentally relevant. And to address that, we try to test it computationally. So we look at the outcomes from training deep learning systems using these types of data. So overall, the data set has over 500 hours. Infants are 2 to 24 months. And we divided them into 3 groups, 2 to 4 months, 6 to 8 months, and 10 to 12 months. So we just use those data. And this is particularly motivated by different developmental stages. So over here, they're mainly in a crib or not mobile much. We see a lot of ceiling fans here in this 2 to 4 months. 6 to 8 months, things start moving a little bit. They're shifting, they're playing with the objects, a little bit more rich visual environment. And 10 to 12 months, they're crawling there everywhere. Things are changing much faster pace. When we just analyze the temporal properties, this is really, really slow. Like semantic properties of these images, if we do like clipping batting on them, if you look some semantic vectors of these images, they're super slow. Here and here, they're already much faster. Now, we trained deep networks with these data, and we tried different configurations, including generative, predictive, and contrastive. This is one example of a generative network. So we took the videos, we took like a cube, let's say 1 second of the video, so a lot of frames, and then we masked some of the voxels in that frame, and then, or in that set of frames, and then we tried to reconstruct that. So the objective function for the deep network is to reconstruct those missing voxels. The idea there is that this will lead to a good embedding. It will learn some properties of the visual world, and we can then evaluate that using what people call downstream tasks. So we can then use that pre-trained neural network and just add one more layer like a linear classifier and train it to do some other tasks. So there are some standard benchmarks in machine learning that we can use to evaluate whether this particular training regime was effective or not. We also tried predictive and contrastive as other types of loss functions. And as evaluation, we used some standard data sets, in particular action recognition, and this toy box. This is kind of objects that infants often play with. And as I mentioned earlier, we divided these into 3 age groups. So we call it G0, 2 to 4 months, G1, 6 to 8 months, G2, 10 to 12 months. And if you look at the performance, I'm just going to give you a quick gist as a kind of main highlights. It's after training just on one age group, so G0, we get the best performance on this self-supervised. After self-supervision, we are evaluating on these data sets, we get best performance for G0 opposed to G2, so the oldest, opposed to G adult, which is also data from adults, like very similar adults wearing egocentric vision cameras. And also, green one is the random. Green one has some frames for each group. So best performance from the G0 Then if we continue training in this developmental curriculum, so after G0, we continue training the network with G1, so give it sort of developmentally next stage of the data, versus if we do anti-developmental, so the G2, oldest group data first, then younger group data next. So we kind of train the network in the opposite order. That does not give good performance. And if we continue that, so this is G0, G1, G2 in blue, giving us best performance, and these other networks just not reaching that high performance. This was also consistent across these different data sets. I won't go into details, but this is mainly action recognition, object recognition types of data sets. In general, we saw benefits from training in the developmental order, which is most likely due to the fact that those data are the slowest, so they are kind of easiest for the network to pick on, to exploit first, learn where it's kind of easy to learn, easier to build prediction or reconstruct the data that are slower, and then gradually adapt to the faster data. So developmental curriculum outperforms all of the curricula after every stage of training. Yes?
Did you say that for like the resolution of the body of the images across all the bases, is it the same? So
Resolution, like resolution of the image itself, it was always the same. It was always same camera.
oh, so do you guys have any plans to maybe modify the like earlier data to be more like aligned with the individual systems, reflective or not rapid?
That's a great question. In collaboration with Justin Wood, we're working on something like an artificial retina that would basically build also this developmental component of having much higher blur in the earlier stages of development. That's a great point.
Who did you say?
Sorry?
Who did you say was working on this?
It was in collaboration with Professor Justin Wood at Indiana University. Second project, for just a quick shout out, Model versus Baby. It's a developmentally motivated benchmark for out-of-distribution object recognition. This is also in collaboration with Linda Smith. The basic question here is how do we learn to categorize objects? This is kind of easy. This is a little harder. If I ask you which of these is a dog, as human adults, I don't think you'd have much trouble. But if you ask a deep learning model, can they also do this? Or if we ask a 2-year-old, can they also do it? That's, I think, more open question. So within that, we created Model versus Baby. It's a data set. It's developmentally motivated object recognition benchmark, and we did some evaluations, so I'm going to show you these in just a few slides. So the data set itself is based on the babies, it's based on answers from 2-year-olds. What they see is they get a book, they come to Linda's lab and they get a book. Each page of the book contains 6 objects, something like this. Those objects come from 8 common categories, and they come under 5 conditions. So some pages of the book, they will be like this. So this is the silhouette condition. Some pages will just have realistic images. Some pages will just have geons. Some pages will have blurred, and some pages will have features. And then the caregiver asks the child, okay, point to a dog. And then the 2-year-old does whatever 2-year-olds do. They sometimes point to the thing, they sometimes don't want to collaborate with you, but nevertheless, they do reasonably well. In general, they are able to do the task. If you look at the performance, it's not surprising. They do best for the realistic objects, so they're able to recognize those best. When the pages contain silhouettes, then they do almost as good. Geons, not so good, blurred, not so good, and features not so good, but still well above chance. Now, we were wondering, we designed this as basically as a benchmark, and we wanted to see how deep learning models do on this. And kind of coming to it, we thought, well, especially geons and things like that, they seem like, well, this is pretty hard. Geons are difficult. It's just, these geons are constructed of 3 pieces trying to resemble the object. So, I don't know, I wasn't too optimistic, but it turns out that these large models, these are in particular clip models, so this is basically the same what ChatGPT is using if you upload an image and you ask it to describe the image. That's the same type of a model. It's trained using contrastive learning, using labeled images. So they embed images and text in, they try to embed it in a space that they become as close as possible. If they're labels of that image, if they're not, then as far as possible. In general, these are pretty good. If we take I'm sorry, these are very small, but the x-axis here represent the model size, so these have a lot of parameters, and they basically do almost perfectly on every category. So deep learning models can do this way better than the babies. interestingly, smaller models, to some degree at least, resemble performance of the baby. So in general, they do well for the realistic over here, and they do also somewhat better for silhouettes than for the other categories. We're still looking at this across the layers of the model and across the training stages. So we are, at least for some of these smaller ones, we can train them from scratch by us and just look at how performance changes over the stages and also how it looks across the layers. Yes?
How do you define the chance levels here?
Oh, this was just a forced choice. So I think they have 6 categories, so it is always a forced choice. Has to be 1 out of 6. Our last, and I'll be very brief, comparing perceptual judgments in large multimodal models and humans. It's also, basic question is related to how do we learn to categorize objects. This here is a picture of a rock. It's another rock, one more rock, rock. But apparently these 6 rocks are coming from 2 different categories of rocks. One is granite and one is diorite. I don't know much about that, but geologists do. And one person who also learned a lot about this is RuCCS. And IU, he did a series of behavioral experiments on humans to evaluate perceptual dimensions that people use to learn categories of rocks. So this is really interesting from the perspective of learning human perception and then later on memory and learning as well. How can we classify these? People can do this. You can train people relatively easily if you give them examples to classify these. And then by using a lot of behavioral data, Rob was able to identify sets of perceptual features that people in general use to classify. So what basically, when you see this rock, you can imagine that your brain is representing it along these types of dimensions like chromaticity, darkness, lightness, disorganized, organized. It's going to be a point in that space. And then some other rock is going to be a point in that space as well, and then based on that, you're going to try to classify them. So these pixel inputs are going to be turned into points in this particular feature space. And Rob has a set of wonderful papers on this. We wanted to see how do deep networks do if they get the same inputs. Are they going to use similar or different perceptual spaces? In general, can they map from these images onto this perceptual space? So we compared perceptual judgments with perceptual judgments in large multimodal models. So this is basically the same. It's again that clip style models, just like ChatGPT, like quite literally we use ChatGPT and some other models in this. We put the same prompt as we gave to, as was given to humans. So basically here's a rock, rank it along some feature, like chromaticity, rank it between 0 and 10. Here's a rock, rank it along the darkness, lightness, 0 to 10. Organized, disorganized, rank it 0 to 10. So the same prompt that the people see, just to rank the feature, rank the rock along that feature. There was another condition also where they provided some anchor images, so a few examples, like this is an example of a dark rock, medium rock, light rock, to see if that improves the performance. This was also done with humans. They also had some experiments where humans got these anchor images. When we look at the performance, we are directly comparing humans to GPT. So each blue dot over here corresponds to an individual rock. X-axis is the value that ChatGPT gave to it in terms of chromaticity between 1 and 9. And this is a human value for that same rock. So in this case, for chromaticity, we can see that they're correlated. And if we look across many other features, general tendency that we see is that they're correlated. We try to extrapolate a little bit whether this is good enough to say replace human participants. So if we want to do a perceptual judgment study, can we take objects and then ask ChatGPT to give us perceptual features of those objects? It's, I would say, almost there. We had one kind of annoying thing with this, or a good thing maybe, is that as we finish evaluating one model, the new model is already out and is doing better than the previous model, so we can kind of just, we still consider this as a benchmark so people can go and improve and use better models on it. In general, the performance is very, very close to an average human participant. We compared several different models. Actually, adding these anchor images did not help much. In some cases, for the GPT-4, that was our best performing model. With or without anchor images is a very small difference, and overall, Overall, GPT-4o, the one that came more recently, I don't have that in this figure, but that one is performing even better and getting very, very close to the human participants. So I'll finish with this. Thanks to all of the PhD and master students, collaborators, and of course the funding sources, and thank to all of you for your patience. Thank you.
So in the last rock learning study, are you studying one resemble about rocks? You're only providing us the pictures of rocks, is that correct? So
Participants are only provided with one picture of a rock at a time, and then they're provided with the next rock.
yes, but they are pictures of rock, not actual rocks. So what makes this model multimodal?
Multimodal in a sense is just vision and language. So maybe the more common name would be vision and language model because multimodality here is just two. Yes.
Yeah, I have a question, for example, in the case of the center of the perception. What is the advantage of this kind of model, for example, to tell us about how we have these representation times? One of the debates, for example, in dissection is that it could be like a logarithmic version of the time perception or a linear one, and there was a lot of debate about like each one representation is the correct one. And for example, in the case of the dissection, this is represented in like geometric meaning that animals and
Exactly, that was the main driver for us was to capture the values. Because we wanted something that can ultimately generalize across different conceptual domains, including time, which effectively all, except for the angles, which are so-called, obey Weber's law. So the logarithmic compression was sort of the essential feature. And historically looking, this type of model evolved from temporal context model, out of HANA 2002, where they had one single exponential became a trace. That was a really good model in terms of explaining phenomena like temporal contiguity in free recall. It was easy to, if I give you a list of words one at a time and ask you to repeat them, like absence, hollow pupil, river drowning, campaign helmet, and I ask you to repeat that list. If you remember some word from the middle of the list, you're more likely to transition to a neighboring word. So you have that conditional response probability looking like something like this. Now, given all that, temporal context model was really good at capturing those temporal effects, but it was limited when the inputs are more complicated. For example, if the input is some complicated time series, like I say, table. With temporal context model, you have one exponential decay traces you can't capture. With these types of multi-trace models, where you can effectively construct a low compressed version of your actual input, it really seems like something similar to perception. Meaning, when we think of the past, we really have this sort of sense of what happened when. It's much more rich than, say, just a set of discrete events. It seems like there is like a temporal structure somehow organized, and on these experiments, like judgment of recency, judgment of imminence, it seems like we can really navigate it. And then the question is of what's the form of it? Is it logarithmic or linear? Then I think the Weber law is a really important constraint that one really has to take into account when thinking of how to space out the receptor fields. And then neural data also is consistent with that. There was a recent paper by Ray Kao from Mark's lab where they did hierarchical Bayesian modeling to basically try to infer what would be an actual functional form of this decay, arguing for a power law decay, so arguing for a scaling invariant function. Yes?
Yeah. So I really like the data set you sort of just give us a taste of at the end, especially how you sort of captures what they see and what they're exposed to. And there's a sort of similar, very similar effect with respect to hearing. Right? So for the first, hearing kicks in more or less at the station, but it's really one of the low frequencies. So if you think of those as sort of being with the covers positive, those low frequencies, those slow things, you got those first 16 weeks in utero of positive, or these slow changing things. Then you go 40 weeks, then you start getting a higher frequency more rapidly far side, right? So if you're looking at things like, ceiling fans, we're actually going to see it with fairly good resolution. So that's something I think we have to read it and not that is my purpose.
I'm really glad you brought these points up. This is some of the things that didn't make it in the 60 minutes of the talk, but we are actively looking into spoken words as well, because we use cameras and microphones. And I would love to talk more actually later about exactly these stages.
She just at 3:30, but if you're still around, you're done at 5:30.
Yeah, we'll catch up. Because what we tried so far was characterizing the number of objects that they see. So the number of each object that they see, for example, how many times do they see a table, a chair, a bed. We can use large language models to literally tell us for every frame what's in there. And we have these distributions for every object. In particular, look for objects that are in the MCDI, that are within the sort of scope of what infants learn throughout the early development. And then we try to look also at how many verbal utterances of those objects are in the data set as well, and do they correspond to the visual. So how many times do the labels come in? So this is really interesting because on one side, well, you see, okay, table is seen many, many times. It's only spoken about a few times. Yet infants will be able to recognize and generalize very well. Assuming they're using the visual, the perhaps temporal slowness to learn that there are these categories of objects that look like this, and then when somebody speaks about it, they're able to relate it. So we're trying to understand a little better what is actually predictive of age of acquisition for these objects. Because we know for each of them what's the, say, 50% age of acquisition for the kiddos. So we can see whether we're trying to see whether their vision, the number of objects that they see, is a better predictor than the number of objects, the number of verbal utterances for those objects. So what you mentioned is very relevant in terms of how their hearing perception, but also the visual perception in terms of the things that are harder might actually be better seen by them. The large language model doesn't know that, they're just asking to label the image, so we are definitely adding some noise into that way. Also for the verbal, you just have a microphone and then do some speech to text and then use that. So there are definitely noise as well. But we are trying to characterize this, and we have now this extrapolation of seen objects and the spoken words for the infants throughout development. So for different stages, it's like a little web page we're going to release very soon, where one can see what's our extrapolation of how many times has an infant seen a table from 0 to 2 months, from 4 months, etc. And then similar for the verbal labels, and then trying to infer what's the actual predictability of that in terms of the age of acquisition. So thank you so much.
Yeah, I have a question for yes, I'm just really curious about a really interesting talk. I'm really curious about your future direction, the way you're integrating the machine learning side of things and the human data and animal data is to look at how efficient those scale invariant representations are and how can that improve performance in reinforcement learning framework. So how about thinking about the other direction, what are do you think insight from on the what kind of task those representations work well, and the cases when it doesn't work well, what kind of insight I can bring back to understanding the human behavior data and the animal data?
Thank you for that question. It's I mentioned a little bit about the limitations that we have right now with building these structured representations. We were built with the primary goal of getting sequential activations in the brain. Historically, there were place cells. Everybody was very excited about place cells, defined fields at different spatial locations. And then time cells came about. There was 2009. There was a paper by Louis Jacques and Professor Paul that they were noticing these sequences of neurons, just temporal sequences, and how that came on and continued on that. But with a number of other physiological recordings in temporal sequences. And this kind of fitted nicely into the computational modeling method. So the goal was to build cognitive models, but also on a neural level. And at the same time, try to capture neural activity and behavior. And then in parallel, we're trying to expand and see, okay, if we try to really do this into systems that learn from scratch, like deep learning systems, what can it actually help us to better understand the cognitive side of it? Can it help us to improve the AI systems? And there's still very big discrepancy there because on one side, these are systems learning from scratch, and I think that Power's task I was showing, we're training encoder from scratch. We're assuming that our artificial rat has never seen anything in its life. And at the same time, it's learning how to do this task, right? It's learning, has this reinforcement objective, and the only feedback it ever gets is whether it not got a reward for turning in the correct direction, because there are more powers on the left and the right, and that's the network that has never ever seen anything in its network life, meaning that all the weights were completely random. So there's the challenge, I think, and the way the field is also seems to be progressing towards is you, at least in the AI, the domain is using these, say, clip embeddings. So you have clip embeddings give you semantic representation for any image. So I give you an image and it will give me basically information about what's in the image. So I can use that as the input rather than having a system that's trained from scratch. People are using that more and more in conjunction with large language models, doing systems like that. But for me, the more interesting part is this representation part, where if we have structured representations, what are the more efficient ways to use that? Meaning, we can generalize pretty well from one domain to another, and if that might be because we are using the same type of coding scheme to represent different domains. Yet that's really not there in deep learning systems. So it would be nice to expand the more general these types of models and systems to take advantage of the structured representations. And yeah, so we hope to go into that way, but also looping it in a sense that these are reinforcement learning agents, but they only emit actions towards how they move in the environment. What they could also do is to emit actions how they move internally. Meaning, if they have structured neural representations, you can imagine like an inner eye, in some sense, navigating these types of structured representations, accumulating evidence and then taking action when there is enough evidence to take an action. So these would be more like cognitively motivated systems that really take into account, okay, there's an internal action of me moving along some dimensions, accumulating evidence for a particular hypothesis, and then making a decision once I have enough evidence. Very different from existing machine learning methods, perhaps not the best in terms of one whole goal would be machine learning, but in terms of modeling cognitive systems that might help us make these AI and cognitive models a little closer.
You earlier to your GPT comparisons, you said that it's not good enough to replace human participants. What is the cutoff score that you guys have to replace human participants?
That's a great question. So we were really looking at distributions in terms of how in individual humans differ, because all of those dots that I was showing on that plot, they were averages from a number of human participants. So we were trying to see, okay, is the GPT going to be a representative of that average? Can we just say, well, we don't need human participants for this task anymore. Can we just use the GPT score? Not very close with GPT-O, not exactly. But if we take it as one participant, then it's more representative of that one participant. Because participant itself, it's more noisy, right? It's like a sample from the distribution. So it's not exactly at the mean, and exactly what, like your question is fair, like what do we put as a threshold? So we don't have some firm metric of like, is it really there? It's really more like how, for whatever is the purpose of using this further, and say in Rosovsky's case, the purpose is using this for models of learning and memory. So is the noise or error that's going to be introduced by, say, ChatGPT instead of human participants going to be meaningfully impacting when he, compares exemplar and prototype models of recognition in his systems? Like, is that discrepancy going to be significant or not?
Yeah, so I have a question. I comment this from a neuroscience perspective, but thinking about errors in memory, right? I think very often we get excited by how well our models do and compare the learning curve if it's faster, better, performs better. But have you thought or maybe know about the types of errors that your model makes? And thinking very specifically, maybe all the way back to your letter order task, right? So if you have this logarithmic compression, it implies that the further away in time, the more error variability around what the actual representation was. That would be a thing. Does that come out in the model and do you visualize that? Yeah.
That's a
pretty
really
cool.
great question. And along the same lines, I think it's very interesting where what is the response time or when they make the error. And surprisingly, or not surprisingly maybe, but if you think of it from a timeline perspective, if I'm comparing, we have G and T in our example, so if I'm scanning and I somehow missed G, maybe I made some encoding error, G was not there, I was distracted, and I keep on scanning, then the model would predict that my response time in those error trials will depend on how far in the past is the less recent item. So it will not depend on how far in the past was the more recent one, but how far in the past was the less recent one, because I kind of missed this one and just continued scanning. And that's really what happens. So we really see that the response time when on the correct trials is flat, so when we test the slope of the regression line, it's flat for correct trials for the more recent one, and similarly, even though there are fewer incorrect trials, just because usually participants here get maybe 70% correct, it's still on the trials that are incorrect, it looks like they're just scanning until that incorrect one and then press the button. So on the computational model, you can say, well, there is a timeline that, yes, you made some encoding error and you don't really have a particular model of how would that happen. But assuming that happened, then the scanning would continue until sort of the match is found, and in this case, it would be the less recent.
Related to that, kind of thinking about things that happen in memory. So one of the things that, in terms of ordered list, there's a privacy and recency effect, right? So is that explainable at all using this logarithmic, like decompression scale or compression scale, or is it some other process happening?
Yeah, it's a great question. Recency somewhat falls off naturally because more recent past is simply represented the more dense receptor, so there's more probably on the second.
So I guess it's the primacy, which is the question.
It's
What
primacy.
explains primacy?
Yeah.
Right, the first letter we saw.
It's a really, I think, different ways how people account for privacy. Usually it's usually just to put in the models as like, and then we add privacy.
That's fair. Yeah, that's fine. You don't have to explain everything in one model, but I was just wondering.
But it is usually considered as some sort of effect that's not under the scope that's even, that these types of models even have power of appendix.
Sorry, I have kind of a technical question about the slide that's in front of us. So, in these cases, the human judgments, these are naive humans, and we're just showing examples.
Yes.
So, when they're judging something like, pegmatic structure or something like that, they're not experts, they're not
They
geologists.
were given a description, and we gave the same description to the LLM. So they were given a verbal description of what has that meaning. That description was written by geologists. This one originated because there was a subsequent room and a neighbor who's a professor in the geology department.
Right, so the ChatGPT and the humans are on the same level playing field, they both have the same information.
Yeah.
Neither of them are geologists, so there's still an open question as to how correlated either of them are with the so-called ground truth from the knowledge.
That's a great question. And I think in this context, we were really trying to understand the perceptual judgment features from a native human, but it's absolutely valid research question in terms of thinking of it from the perspective of, okay, these are rankings from a geologist, what could happen? One could even argue that ChatGPT might be a geologist to some extent, given that actually you just ask it about these types of properties, people tell us a lot. It would seem like it's a pretty good geologist. So I think we did some prompt engineering for this paper where we tried to tell, okay, you're expert geologists to answer these questions. It didn't change much in terms of the answers, at least for the ChatGPT, but for humans it might. Human geologists might have a better intuition of what do some of these features mean. So that's
but nobody thinks you could turn a naive human into a geologist by showing a few images and a few little descriptions.
Yeah, there definitely would be a different. Thank you.